Hello and welcome to another video. Today we will be learning about rational functions and their end behavior. First, let's look at a rational function. A rational function is a quotient or a fraction of two polynomials. If you look here, you have a rational function y equals f of x divided by the function g of x. Again, f of x and g of x have to be polynomials, and g of x can never be equal to 0. Please remember that when you have a fraction and you have a 0 in the denominator, you will always get an undefined as an answer. So if we do that when we have a fraction, then you actually can never create a graph because every single point in the graph will be undefined. The same thing if you try to create a table. So here we have some examples of rational functions. The first one is y equals 2 divided by x plus 3. Don't forget, you can rewrite that as 2x to the 0 over x plus 3. Now you can see that you have polynomial in the numerator, and then you have also a polynomial in the denominator. This is another example. Again, I have a polynomial in my numerator, x squared minus 3x plus 1, and then I have a polynomial in my denominator, 3x plus 4. And then one last example. Again, I have a polynomial in my numerator divided by the other polynomial in my denominator. Before I go into this information here, I want to look at some rational functions graphs so that way we can notice some things, so that will make our lesson a little bit easier. So here I have a rational function, and on this rational function I have a horizontal asymptote that I'm going to highlight in red. I also have a vertical one here. We will talk about those later, but for now I'm just going to do the same thing and put it on red. Again, we're talking about rational functions and their end behavior. So if I look at this graph, I can actually see this graph, and I can see I have an arrow pointing to the left, and I have an arrow pointing mostly up, arrow pointing down, and arrow pointing to the right. When we're talking about end behavior, remember we're talking about the far left and far right side of the graph. So in this case, when I do my end behavior, I'm looking at the left side here and the right side here. This arrow going up and this arrow going down are in the middle of my graph, so I'm not going to pay any attention to them for this lesson. But again, we will come back and talk about those later on. If I look at the left side, I can see that as I follow my graph to the far left, I'm getting closer and closer to the asymptote. As I keep going farther and farther into the left side, I notice that I get closer and closer, but again, I will never cross the asymptote, and I will never actually get to the asymptote. That is y equals 1 in this case. So again, since I'm getting closer and closer and closer, I'm never actually touch it or cross it. I am going to say that the limit as x approaches negative infinity for f of x is going to be equal to 1. I'm going to look at the right side, and it's going to be similar. I follow my graph all the way to the far right. Again, I get closer and closer and closer to the asymptote, but I never get there or touch it. So I'm going to say the limit as x approaches positive infinity of f of x is equal to 1. In conclusion, every single time that you have a horizontal asymptote in a rational function, the limit to the left and the limit to the right will be equal to that asymptote. In this case, I can see that the limit as x approaches negative infinity for f of x is 1. I can see that the limit as x approaches positive infinity for f of x is equal to 1. And I can see that my asymptote is y equals 1. So this is kind of like scenario number 1 when you do have a horizontal asymptote. Scenario number 2 looks something like this, where I don't have a horizontal asymptote, but in this case I have a slant or oblique asymptote denoted here by the red line that I'm about to draw. I also have a vertical one, even though it wasn't given to us. I'm just going to add that really quickly. Same thing, I am looking at the arrows that will give me the far left of my graph and the far right of my graph, which I highlighted in green right here. So I'm going to do the same thing. I'm going to follow my graph going to the far left. right here, following the highlighter. And again, I can see that I'm getting closer and closer to that red line, but I'm never actually going to touch it or cross it. But it will follow along in the same direction that the line is going on the left side. So I'm going to say that the limit as x approaches negative infinity for g of x, I will call it g of x, is equal to negative infinity. Again, I can see my line keep on going. It will keep on decreasing without bound, which is kind of similar to when we were doing polynomials and their end behavior. So again, I can see it decreasing, decreasing, decreasing. It will keep on decreasing forever. So I'm going to say that my limit is approaching negative infinity. When I look at the opposite side, I'm going to say that the limit as x approaches positive infinity for g of x is equal to positive infinity, because as you can see on this part of the graph, it will keep on increasing without bound, or it will keep on going up forever. So keep in mind, if you have a horizontal asymptote, again, all you have to do is find the horizontal asymptote, and then you automatically have the limits. If you don't have a horizontal asymptote, your answers will always be either positive infinity or negative infinity, depending on what way the graph is behaving. We will talk a little bit more about this case during the lesson, but those are some important things to remember. Okay, so back to our lesson. You can find the end behavior if you have a horizontal asymptote very easily. So we are going to talk about two different cases where you have a horizontal asymptote just by looking at your leading terms in your numerator polynomial and the leading term in the denominator polynomial. So that's what this part is talking about. You will create three different cases. The first case says that the denominator dominates the numerator, or the exponent in the denominator is bigger than the one on the numerator. You might have heard that as bottom heavy function. And then I'm going to give you an example. So that might look like y equals 3x squared minus 4 over x cubed minus 8. So when we look at this equation, we notice that the exponent at the top, the highest exponent at the top, or my degree, is going to be 2, and then the one in the bottom is going to be 3. So the denominator has a larger degree or has a larger exponent. So that's what's going to dominate how the function behaves. So in this case, if I plug in a really huge positive number for x, and then I square it, multiply by 3, and subtract 4, it's going to have less of an effect on the number than if I take a really huge number, cube it, and then subtract 8 from it. Graphically, your number will be growing faster on the denominator, meaning that your number will get smaller and smaller and smaller as you're plugging in numbers, creating something that looks like that, and then you're approaching 0. Again, it doesn't matter how big this number is, you will never go into the negatives. So that's why your horizontal asymptote, when this situation happens, will always be y equals 0. And that's what it's saying here. This is kind of a lot to remember, so you can remember this acronym, BOBO. And BOBO is going to stand for bigger on bottom. And then the second O again represents the 0 answer. When we're talking about bigger on bottom, again, we're talking about the degree or the highest coefficient. So I'm saying the degree is bigger on the bottom, or the degree is bigger on the denominator. If this is the situation that you have where the denominator has a larger degree, then your answer will always be y equals 0. Please keep in mind that when we're talking about horizontal asymptotes, it has to be an equation. So if you're taking a test and they ask you for the horizontal asymptote and you put that your answer is 0, your answer is technically incorrect, because again, when you're talking about a horizontal asymptote, the answer has to be in the form of an equation. So if you say y equals 0, then you have the correct answer. Again, for case number 2, you also have a horizontal asymptote, but in this case, the leading terms are going to have the same degree. If you do have that, then you're going to have to divide the leading coefficients for both the numerator and the denominator to get your horizontal asymptote. An example, y equals 3x squared minus 8 over 4x squared minus 3. Again, we look at the degree. So the degree in the top is 2, the degree in the bottom is 2. So based on this, I can find my horizontal asymptote by dividing out the leading coefficients. So in this case, the leading coefficient for the numerator is 3. The denominator leading coefficient is 4. So the horizontal asymptote will be y equals 3 over 4. For this one, I'm going to have my acronym Betsy, bigger, bigger. I'm sorry, bottom equals top. And then the C is going to represent the coefficients that I divided. So when I do this, again, when I'm saying bottom equals top, I'm talking about the degree. The degree of the bottom equals the degree of the top. The degree of the denominator is equal to the degree of the numerator. When that happens, to find my horizontal asymptote, all I have to do is divide the coefficients by each other. Case number 3 is going to be the hardest one because this one you don't have a horizontal asymptote. So you know that your answers are going to be positive infinity or negative infinity. On this case, the degree of the numerator is bigger than the denominator. So an example of that would be, get some different color here. Y equals x cubed minus 3 over 10x squared. Again, all we care about is the degree. So looking at the numerator degree is 3. Looking at the degree of the denominator is 2. The one on the top is bigger. When that happens, you have to look at the end behavior of the polynomial that will be given to you by this. So this is the division of the leading coefficients, and then this one you're subtracting the degree of the numerator divided by the degree of the denominator as your exponent. Please make a note that if the degree of the numerator is exactly 1 more than the degree of the denominator, then f of x has an slant or oblique asymptote, which is what we saw at the beginning of the video. You can see here that the degree of the numerator is 3, the degree of the denominator is 2, their difference is 1. So this example right here will have a oblique asymptote. And you must do long division to find it, which we will do in the near future. Last acronym that you have to remember for this one, it's going to be BOTD or BOTD, bigger, on top. And then I like to use the letter D to represent does not exist when we talk about horizontal asymptotes. And it also helps me to remember that I need to divide to find the equation for the polynomial that will determine the end behavior. Okay, let's look at some examples. Example number 1 says determine if the following rational functions have a horizontal asymptote, slant asymptote, or neither. If the function has a horizontal asymptote, write the equation of the asymptote. So I'm going to go fairly quickly over these. First, I'm going to look at the degree of the numerator and the denominator and then compare them. So for A, I have a 2 as my degree for my numerator. I have a 2 as the degree in my denominator. So they're equal to each other. So that reminds me of the Betsy situation, bottom equals top, where again, the degree on the top and the bottom are equal to each other. And then it tells me to look at the coefficients. So that's what I'm going to do here. My leading coefficient for my numerator is 3. The leading coefficient for my denominator is 5. So I'm going to divide them. And again, it has to be in the form of an equation. So in this case, it's just going to be it's going to be y equals 3 over 5. Looking at B, I have my degree at the numerator, which is an imaginary 1. Again, I don't have to put it, but you can add it to make this process easier. The degree in my denominator is 2. So the 1 in the bottom is going to be bigger. So that reminds me of the case number 1, or bigger on bottom. And then again, the last O represents my answer, which is going to be 0. So I know that for this one, based on the bubble rule, or case number 1, my horizontal asymptote is going to be y equals 0. Looking at C, Again, I'm looking for my degree at the numerator, which is 2, the degree on my denominator, which is 1. So it's bigger on top. This is going to be the Bode situation. Again, I do not have a horizontal asymptote, but I do have a asymptote that is kind of have the same behavior as a polynomial of their divisions. So if I do 2x squared over 5x and simplify that, that will give me 2 over 5x. Again, this is going to be a linear function, so this is going to be a slant asymptote. Okay, looking at D, I have a degree of 1 in the numerator, I have a degree of 1 in my denominator. So again, they are equal to each other. So in this case, I am going to look at Betsy, bottom equals top, and then divide the coefficient. So y equals my leading coefficient at the top, which is 4, leading coefficient in the denominator, which is 8, and then that's just going to simplify to 1/2. So y equals 1/2 is my answer for D. Looking at E, I can rewrite this as 3 times x to the 0. Now I see my degree in the numerator is 0, my degree in the denominator is 2. So it's bigger on the bottom, or the degree is bigger on the bottom. So that reminds me of the bubble rule. So I know that my answer for this is going to be y equals 0. Looking at F, negative 4 over 2x plus 1. So again, I'm going to rewrite the numerator as 4 times x to the 0. So that's going to be my degree, and then that's going to be my degree in the denominator, which is 1. Again, the denominator or the degree is bigger on the bottom, so I know that my answer has to be y equals 0. Okay, looking at the next example is asking you to write the limit statements to describe the end behavior of the following rational functions. So for A, I'm going to look at my equation, look at my degree. The degree on the top is 3. The degree in the denominator is 3 as well. I can see that they're equal to each other. So again, it reminds me of the Betsy rule, bottom equals top. And then again, the C reminds me that I must divide the coefficient. So since I'm using the Betsy rule, I know that I do have a horizontal asymptote. So I'm going to make a note here that I do have one, and it's going to be y equals the division of the leading coefficients. So in this case, it's 2 over 6, which simplifies to 1/3. As I told you before, if you have a horizontal asymptote, the limits to the left and the limit to the right will be equal to the horizontal asymptote value. So in this case, I'm going to say that the limit as x approaches negative infinity for f of x is going to be equal to 1/3, because that was my horizontal asymptote. For the right, it will be something similar. The limit as x approaches positive infinity for f of x will also be equal to 1/3. So look for the horizontal asymptote. If you do have a horizontal asymptote, then automatically the limit to the left and the limit to the right will be equal to 1/3. Okay, looking at the next example, again, I'm going to do the same thing. I have a degree of 2 in the numerator. I have a degree of 3 in the denominator. So in this case, the degree is bigger on the bottom. So again, that reminds me of the bubble rule. So I'm going to say I do have a horizontal asymptote, and it happens to be y equals 0. Since I have a horizontal asymptote, I know that the limit as x approaches negative infinity for g of x will be equal to that asymptote, which in this case is 0. And then the limit to the right is going to be y equal. The limit as x approaches positive infinity of g of x is going to also be equal to 0. Okay, next example for C. My numerator has a degree of 4, my denominator has a degree of 3. So in this one, I don't have a horizontal asymptote, so I'm going to make a note of that. And then I'm going to divide it. So negative 3x to the 4th over x cubed. So when I simplify this, I get negative 3x. So I know that the limit will behave like the function y equals negative 3x. So this one I know that it's going to be a positive infinity or a negative infinity for both of my limits. If you remember from the last lesson, this is a polynomial. So we're going to use what we learned last time to figure out what the limits are. I'm going to start by looking at this function, for this polynomial and noticing that this is an odd degree polynomial. So I'm going to make a note that it's odd and it has a negative leading coefficient. So if I remember from last time, I told you to just remember one odd function that has a negative leading coefficient, in this case y equals negative x cubed. So I can look at this function and get my limits from here for my rational function because the limits will be the same. So if I look at the limit on the left side, I know that I'm increasing without bound. So the limit as x approaches negative infinity is going to be positive infinity. And then if I look at the limit to the right, the limit as x approaches positive infinity is going to decrease without bound, meaning my limit is negative infinity. So I'm just going to write those very quickly. Left limit as x approaches negative infinity for h of x, again increasing without bound, is going to be equal to positive infinity. And the limit as x approaches positive infinity for h of x is going to be negative infinity since it's decreasing without bound. For example, D, you are looking at a rational function graph and determining the limits. So here I'm going to do what I did at the beginning of the video, highlight the asymptote, which in this case is y equals 2. After that, I can see, like I said, that the left side is approaching the asymptote and the right side is also approaching the asymptote. So I know that the asymptote and the limits will be the same number. So I'm going to say the limit as x approaches negative infinity, I'm going to call it f of x, is going to be equal to 2. And then the limit as x approaches positive infinity for f of x is also equal to 2. Okay, looking at E, I have this function, and then I also have a horizontal asymptote here that I'm going to highlight, and it's going to be y equals negative 1. Again, I can see my graph is approaching at the far left the asymptote, and then same thing on the far right. So I know that my limit to as x approaches positive and negative infinity will be equal to negative 1 in this case. So limit as x approaches negative infinity for f of x is equal to negative 1, and then the limit as x approaches positive infinity for f of x is going to be equal to negative 1 as well. We already talked about the slant asymptotes and how to find them. I kind of went ahead and explained that as I was doing the bubble Betsy Balti. So please make sure that you read this. Again, in order for you to have a slant asymptote, the numerator has to be exactly 1 degree greater than the denominator. And then if that happens, then you will have a slant asymptote that it will be parallel to the division of the leading coefficients with an x on it when you simplify it. So example number 3, or your last example, is asking which of the following rational functions has a slant asymptote parallel to y equals 1/2 x. So I'm going to do this fairly quickly, looking at the first one, f of x equals x squared plus 3 over 2x squared plus x plus 6. I look at the degree of the numerator, which is 2. Look at the degree of the denominator, which is also 2. Degrees are equal to each other, so that reminds me of bottom equals top, and then C divide the coefficient. So this one actually has a horizontal asymptote at y equals 1 over 2 or 1/2. Again, I want one that has a slant asymptote parallel to the line y equals x. So I can cancel out A and I can cancel out answer choice D. For the second function, I have a degree of 2 on the numerator, degree of 3 in the denominator, so it's bigger on the bottom. So that reminds me of bubble, so horizontal asymptote y equals 0. So again, I can cancel out answer choice B. For the third equation, I have a degree of 2 in the numerator, degree of 1 in the denominator. So I know I do not have a horizontal asymptote, so I'm going to look at the leading terms and divide them by each other, which is x squared over 2x. When I simplify that, that does simplify to 1/2 x. So this will be a function that has a slant asymptote that will have 1/2 x as the beginning part of the asymptote. So this did work. So that doesn't really help me because I still have 3, and then this one has 3 and 4. So let me check the last one. And then if the fourth one works, then I know my answer is E. If it doesn't, I know my answer is C. So when I do this one, I have a 4 as my degree in the numerator. I have a 2 as my degree in the denominator, so I'm going to do the same thing. X to the fourth over 2x squared. Simplify that, that will give me 1/2 x squared. So this is actually not a slant asymptote. It's going to look like a quadratic function when I look at it. So I know that E is not my answer, so C will be the correct answer. Thank you for watching this video. Hopefully you learned something new today. Don't forget to follow the channel if you haven't done so, and like this video. Thank you for watching. See you next time.